Hello, everyone. Thank you so much for being here. On behalf of the Environmental Finance Center Network, welcome to today's webinar, Stormwater Management Essentials for Small Systems and Communities. My name is Zoe Eisel from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. GoToWebinar has recently gone through an update, and you can now add live captions, raise your hand, or react using emojis. After the webinar, you will receive a follow-up email that includes a link to the recording and any other information you may need. You can also download the slides from today in the Materials tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. One of the many ways EFCN can support your community or utility is through our free funding application support. Struggling with an infrastructure funding application, falling short on project funding, not sure where to start? EFCN is here to help. Use the link in the chat to submit a request and receive tailored support based on your project's needs. And on that note, we can get started. I would like to introduce our presenter for today, Danish Kumar, Climate Change Program Manager from the University of Maryland Environmental Finance Center. Welcome, and I will go ahead and hand it over to you.
Thank you, Zoe. I'll just share my screen. Does this work?
Looks great.
Okay, perfect. Hi, everyone. Thank you for joining this webinar. Let's get started. A little bit about University of Maryland Environmental Finance Center. We offer resources, training, and technical assistance for drinking water, wastewater systems. We also provide education and training and also assist communities with policy analysis and financial assessment. We have some flagship programs. One is called Sustainable Maryland, which is a certification program for municipalities in Maryland. And then the other one is MOST, which is Municipal Online Stormwater Training Center. You can go onto the MOST website and access courses regarding stormwater management. Again, I just wanted to emphasize on technical assistance. Zoe already covered it, but if you want to get technical assistance, you can click on the Get Help form on the EFCN website, or you can also reach out to me via this email at dkumar18@umd.edu. Let's talk about today's agenda. We'll talk briefly about stormwater runoff and urban hydrology. We'll talk about climate impacts on stormwater and what are some nutrients, sediments, and their impacts on stormwater, some green infrastructure practices to protect infrastructure and watersheds, a basic overview of MS4 permits and their requirements, and then we'll have a brief overview of EPA online tools and green infrastructure tools available and resources as well, which is freely available for use. So let's start with a poll.
Looks like most people voted. We have 49% regulatory agency, 10% wastewater system or drinking water system, 19% municipal government, 3% academia, and 20% consultant.
We got quite a nice mix of audience today, and it's really good to see interest from the regulatory agencies in this topic. So let's talk about rainfall runoff. Precipitation rainfall, when it falls onto any surface, has the potential to turn into runoff depending on the surface or the type of land it falls on. It can either infiltrate, as shown in the image, or it can turn into runoff if the surface is impervious, like streets, parking lots, and rooftops, preventing groundwater recharge, and which is not able to being able to soak in any water, and it then goes into a conveyance system via our stormwater infrastructure, which is designed to move stormwater away through pipes and channels into our watersheds and receiving waters. Stormwater runoff and hydrology are really critical components of watershed management, directly impacting infrastructure and environmental health of our local communities. And understanding how water moves in the environment and across different landscapes is really important, and is really essential for protecting both small water and wastewater systems as well as local ecosystems as well. We'll talk briefly about watersheds and stream network. A watershed is an area of land that channels rainfall, snowmelt, and runoff into a specific common body of water, such as river, lake, or ocean. And healthy watersheds provide services like water filtration, high property values. It can obviously increase that, and they also protect wildlife habitat, and they can create opportunities for recreational spaces. Stream networks, on the other hand, describe how water flows in a stream or channel with continuity of water flow. A stream network is also defined by stream order. You can see in the image here that we have different order streams. First order streams, which are smallest, uppermost streams at the very beginning of the network that have no tributaries, and they flow into or converge into second order streams, and then those second order streams converge into third order streams, and ultimately reaching a larger body of water. In an urban setting, a stream network may be disturbed by development, and it can have consequences or impacts for the entire watershed as well. So it is really important to understand how the water moves after rainfall, and understand both the intensity of potential rainfall. We'll talk about that briefly with help of graphs, and the frequency at which these events are likely to occur, like precipitation events. So, as I mentioned, watersheds are interconnected systems. What happens upstreams directly affects water quality and flooding downstreams as well, and even small local actions like increased payment in one subdivision can impact the larger watershed as well. So effective stormwater management is really essential at or critical at watershed scale, not just like focusing into individual parcels. And these healthy watershed provide us really important essential services that we often take for granted. They help us reduce flood risk. They help with reducing pollutants or filtering pollutants, and then they also provide wildlife habitat support and recreation activities. And when watersheds are degraded by excessive runoff because of lack of infiltration, we lose these services, and we must compensate either through costly engineered solutions. So that is why protecting these watershed are really, really important for the environmental and economic priority. So we, in this stormwater management landscape, we hear these terms runoff coefficient. It represents the fraction of rainfall that becomes runoff. Since now we know how the runoff is generated after rains, and it depends on the impervious cover, how much water gets soaks in or how much water is infiltrated. There are different equations used to calculate amount of rain, and there is different type of data available from institutions like NOAA with curves and tables to show that. But for today's webinar, we'll just talk about this simple equation showing you on the image on the slide, and how can we use this simple equation to calculate amount of rainfall generation. And we'll also touch a little bit on another method, which is called curve number method, which is developed by USDA. And you can see in this formula that it shows a linear relationship between impervious cover and runoff. If imperviousness increases, runoff increases proportionally as well. We'll see this with an example in a moment. This simple equation demonstrates why urbanization significantly increases stormwater volumes. Even modest increases in pavement or can lead to increase in runoff generations. So I was talking about a runoff coefficient and how it directly, in this case, it's not always that simple, but in this case, we are taking it as a linear relationship. Different land uses have different impervious percentages or ability to soak in or infiltrate water. Commercial areas may be between 85 to 100% impervious, while open spaces may be under 10%. We can see how these percentages change, and these differences directly translate into runoff volumes and peak discharges. So we can see that that if we are calculating runoff volume for 1 inch of rainfall for a 10-acre area, uh, the area where before development the impervious cover is 5%, we only generate 13,500 gallons of runoff. But if with the same rainfall and with high impervious cover and the same area size of parcel lot, we generate almost 4 to 5 times more gallons of water as runoff. So these really help us understand how land use patterns and land use pattern impact the stormwater runoff generation as well. And we'll talk briefly a little bit about NRCS curve number methods, which similarly reflects how land use, but it also considers soil types, influence on runoff potential. And understanding these like land use patterns helps us planners anticipate stormwater impacts. So this is another method to calculate stormwater runoff volumes based on land use, but it also considers really important consideration of soil, how much soil is saturated for a particular area. This curve number method is developed by USDA, and it is widely used as an approach for estimating rainfall runoff in a small to medium-sized watershed. And unlike simple method, which focuses primarily on impervious percentages, which is used for like small sites, this method accounts for interaction between rainfall, soil types, and land use to determine how much water gets soaked in or infiltrated versus how much runs off. And it is usually useful for bigger sites, rural areas, or flood control. And it helps in sizing of ponds and stuff like that. And it kind of looks at, we can see that to determine a curve number, you'll have to look at the relationship between soil type, A, B, C, D, what the soil type is, what's the land use is in that particular area. You can see that in the table, and moisture. It is nonlinear because it accounts for the fact that dry soil behaves differently than the saturated or soaked soil. And it is usually classified into 4 hydrologic soil groups, A, B, C, D, where A soils, sand, have like low runoff potential, and D soils, clay, which are already, we know, saturated, have high runoff potential. And I have like shown you an example of how to do this calculation for different land cover types. And again, we can see that how different land cover types impact the generation of runoff. Like open green space only generates almost 1,000 gallons of runoff, but similarly parking lot generates like almost 20 times more runoff based on assumptions that I have taken. So it is really important to see like what method we are using, and we have to be careful while using these equations, keeping unit conversations in mind. Like we use rainfall in inch, and we have to convert it into feet, and we have parcel lot size in acres. So we have to keep those conversions from acre feet to doing volumetric calculations in gallons. And here we'll use the similar formula like previous equation for volumetric calculations. Some basic terms that we often hear in this landscape: detention and retention. There's a subtle difference between both of them. Detention temporarily stores water and releases it slowly to reduce like peak flow, and retention keeps water on site permanently through infiltration or harvesting. Retention helps us address flooding, but retention like addresses both flooding as well as water quality because it helps infiltrate the water. And understanding these distinction helps communities what appropriate design strategy to select for their stormwater infrastructure. Another key terms that we use oftenly, peak flow, which is the highest discharge during a storm event. High peak flow can cause like stream back erosions and infrastructure stress. Managing peak flow is really critical to prevent downstream flooding and erosion. We'll see an example momentarily. And engineers often use this rational method formula. Again, this comes with a lot of assumptions as well. That maximum rate of flow is produced by a constant rainfall, which is maintained for a time of like equal time of concentration. And flow attenuation, on the other hand, helps flatten the hydrograph, reducing that peak by slowing the water down. And stormwater managers or stormwater practitioners can reduce the intensity of flow as it enters the stream. Another key term, design storm, we often use in designing our infrastructure. We often hear terms like a 10-year storm or a 100-year storm, and a lot of people can get confused, or sometimes there can be a misconception as well. People think that a 100-year storm happens exactly once every 10 years, but in reality, it actually refers to the probability. A 100-year storm has 1% chance of happening in any given year. Similarly, a 2-year storm has 50% chance annually. So we see how this works like in a probability-based concept. And it is critical because infrastructure must be like designed for risk tolerance, not certainty. Many communities design water quality practices for small, more frequent storms like 1 or 2 years events. But for like flood control, it should be able to, infrastructure should be able to handle 20-year, 25-year storm event or 100-year storm event. But one thing that is complicating all these design infrastructure or parameter is climate change, because that is changing changing our rainfall patterns and causing more intense storms. So we have to think about that. We have a section where we talk in detail about that. And because climate change is changing these patterns, historical rainfall records may no longer accurately represent future risk, and traditional design standards that we use these days can underestimate peak flows and peak volumes as well. So for operators and planners, this raises a really like important questions like how your systems are designed to handle the storm events for like future. And a lot of engineers use IDF curves, which are intensity, duration, frequency curves. We'll learn momentarily about that, which are derived from NOAA Atlas 14 data, which provides precipitation frequency estimates. And NOAA currently is working on Atlas 15, which will hopefully have some climate considerations as well as incorporating like non-stationary data to predict future impacts or future precipitation scenarios and design infrastructure according to that. So this, I was talking about IDF curves. We'll just momentarily or briefly touch on that. IDF stands for intensity, duration, frequency, while there's another graph or term used called depth, duration, frequency. Both describe how rainfall characteristics vary with storm duration recurrence. IDF curves focus on rainfall intensity, how intense your storm is, which is typically expressed in inches per hour for various storm durations from 5-minute to 60-day storm, and like different return intervals. We can see the legend here from 1-year return interval to a 1,000-year return interval. Again, this talks about probability of happening that storm. An example here would be a 10-year storm, like lasting 15 minutes. 15 minutes may produce extremely high intensity, even if the total rainfall depth is not very large. And these short bursts of precipitation or rainfall can determine like if your inlets surcharge or your pipes are overflowing or not. And the shorter the duration, the higher the intensity typically usually becomes. And that's why like this creates a flash flooding situation. And that's why flash storms are are kind of dangerous than the normal rainfall events, because they generate intense runoff in a very short time frame. And our infrastructure sometimes is not able to handle that. Another key term or graph that is used by planners and designers is DDF. Depth, duration, frequency curves focus on intensity to total rainfall depth. Previously, we were talking about flow. Now we are talking about volumes and depth. These curves are critical when designing storage systems, such as detention basins, retention ponds, and green infrastructure. For example, a 100-year 24-hour storm might produce 7 or 8 inches of rain. The total depth determines how much volume your basin must be able to store temporarily, or must be able to infiltrate if it's a green infrastructure temporarily to reduce the runoff. And DDF curves are therefore really essential when evaluating flood storage capacity and watershed scale impacts. Just in summary overview, you should be using IDF curves when calculating peak discharge, especially for storm sewers, culverts, pipes, inlet system, things like that. And you should be using DDF curves when designing storage systems, detention basins, retention ponds, green infrastructure, where we consider or value total rainfall volume. So again, just want to reiterate that these data is based on historical precipitation data and available for every zip code or every location in US on the NOAA website. So let's talk a little bit about climate change and stormwater impacts. Climate change is altering precipitation patterns across the US. We are not necessarily seeing more total rainfall everywhere, but we are seeing more intense rainfall events. Storms are becoming heavier, storms are becoming shorter, and more kind of concentrated. So that means infrastructure designed decades ago based on the historical data may not be fully prepared and could be undersized for current conditions. So because of increased rainfall intensity leads to higher runoff velocity, which leads to greater erosion and higher inflow and infiltration into wastewater systems as well. We have another poll.
We'll give people just a little bit more time to answer the poll. I encourage you to put your answers in. All right, it looks like 67% of people said more frequent intense flash storms. 9% of people said higher total seasonal volumes. Another 9% of people said no significant change noticed, and 15% of people said decreased rainfall/drought periods.
Yeah, that's what we have been observing with the data as well. Like there are more frequent and intense flash storms. We'll see momentarily in next few slides as well. Like uh, the National Climate Assessment shows that heavy rain events, as you all mentioned, have increased in intensity over the past century. We can see the projections in the map above on the right from 1901 to 2016. And then different projections for 1958 to 2016, how they have increased. And I'd like you to pay attention to that. We can see that for Southeast and Northeast, the percentage or number of events is percentages is 27 and 55. But more recently, with the in the next slide, I'll show you the data for till 2021, we can see how even that has more turned into intense storms, and number of events have increased more recently as well. And extreme precipitation happens when a location receives much more rain or snow during a short period of time than normal. What counts as extreme obviously depends on the location and season. For example, some location might frequently experience 2 inches of rainfall from a single storm. However, in other places, this amount of rain might be very rare. So it would be considered like kind of extreme in those locations. In the maps below, extreme precipitation is defined as top 1% of the heaviest precipitation events for an area. These are again based on climate projections on if it's a low emission scenario, RCP 4.5, or if it's a high emission scenario, RCP 8.5, how it will impact the precipitation change in several parts of the US. And heavy precipitation and flooding obviously can overwhelm stormwater systems and affect water quality. In many cities in the US, we have combined sewer systems as well that can carry wastewater and stormwater in the same pipes, and heavy rain can overwhelm these systems, forcing them to release untreated wastewater into local bodies, or these combined sewer overflows containing raw sewage, debris, sediments, and other like oils and hazardous substances can also pose risk to people and environment. We often hear about backflooding into people's basement where there are combined sewer systems and an event of a rainfall. And flooding can also have obviously disproportionate impacts on infrastructure in underserved communities. A lot of water systems in US kind of already experience water quality problems and are in most cases underprepared for flooding from extreme precipitation. Yeah, this I wanted to highlight this, that we can see that from 1958, this graph is more kind of recent till 2021. We can see change in percentage of heavy precipitation events, as you all said, are becoming more frequent and more 37, 30, around 40 to 60 events of heavy precipitation in these northeast and south of US. Again, extreme rainfall or intense storms have implication in older cities with combined sewer systems. Heavy rainfall can exceed capacity and can discharge untreated sewage, as I mentioned earlier. And even in separate system, excessive stormwaters can cause sanitary sewer overflows, and physical impacts we can see in this image includes stream erosion, infrastructure collapse, and can have like economic impacts from the flood events through disruption of, like we can see in this image again, of local businesses and burden municipalities and communities with repair costs. So understanding stormwater control is really like critical to reducing these overflows and infrastructure burdens. And also like extreme rainfall can expose weakness in aging infrastructure. And for small systems, emergency repairs can be like really financially devastating. Why this matters, I'll just skim through it. Stormwater directly affects influent quality in a lot of cases, flows and plant stability. High flow events can cause bypasses, overflows, and permit violations. And understanding this how stormwater moves from one part of land to the other really helps protect plant performance and and protect the watershed which are receiving these waters. So stormwater is not just water, it carries pollutants. So understanding pollutant sources helps target prevention strategies. This slide highlights common watershed threats such as nutrient loading, sedimentation, and contamination. These threats originate from land use practices like we can see in this image, fertilizer application, construction activity, road runoff. When unmanaged stormwater transport these pollutants downstreams, ecosystems can suffer and impair. Water bodies may require like maximum daily load limits, and which can also pose strict limits to wastewater treatment plants, and therefore like upstream stormwater management really can help downstream compliance. This image also highlights point source pollution. We can see from a single identified location, like a pipe or ditch. We can see a discharge coming out from factory, discharge coming out from wastewater treatment plant. These are all point sources which are relatively easy to control, identify, and manage. While like non-point sources pollution comes from different areas across the watershed, like stormwater runoff, which can carry fertilizers from the land, wet waste from the sidewalks, or oil from like streets and debris and things like that into the water bodies. And point sources are, we all know that, regulated by permits, whereas non-point sources pollution is harder to track and often managed through land use practices and best management practices like vegetation buffers and green infrastructure. We'll talk more about that in detail. So again, some pollution sources: nutrients, sediments, chemicals, and pathogens. Organic pollutants like pollen leaves, plant clippings are very nutrient rich, and organic debris can clog these storm drains and leach nutrients into the surface water. Direct application of fertilizers. We all in the winter would have seen during the storm application of road salt, pesticide, pet waste, and like nutrients added to lawns can easily be transported to local streams via runoff, and pollutants can originate again from roads, rooftop, industrial site, etc. I just wanted to plug in like road salting, or like salting your um, sidewalk and how it impacts our waters, because we recently saw a major snowstorm, so everyone would have seen salt on the roads and streets. So road salt is a really significant stormwater pollutant. Chloride does not degrade easily. It accumulates in soils and water bodies, and elevated chloride levels can harm aquatic life and mobilize heavy metals. And we should be using smart salting techniques such as pre-treatment brine application, pre-treated brine application, and like calibrate our equipments to reduce like salt usage, because I was reading that 1 teaspoon of salt can easily pollute like 5 to 6 buckets of water. So it is really important to optimize your salt use in these times during winter especially. So, and this optimized road salting and proper winter maintenance can be considered as a good housekeeping and pollution prevention best management practice under the MS4 permits, if some of you have that, under like good housekeeping for municipal operations. So that's one thing to keep in mind as well. Yeah, back to like how this all impacts. During dry periods, pollutants accumulates on surfaces. When the first rainfall occurs, that initial runoff, casually known as like first flush in some communities, contains the highest concentration of pollutants. Runoff after precipitation kind of act as a vector, picking up hitchhikers like motor oil, lawn chemicals, and sediment into the conveyance systems. And obviously, excess nutrients can trigger algal blooms, which can cause like fish kills, impair your waters, and reduce biodiversity. And this can like occur both in freshwater and estuarine waters as well. So capturing and treating this initial runoff can significantly improve water quality outcomes, and many stormwater-based management practices are kind of designed to address this phenomena. Again, just showing an example of how the imperviousness matters, because we can see an example of natural cover with a meadow with a curve number of 58, we can see the peak discharge being 3.1 cubic feet per second. Similarly, for the similar lot, we can see peak discharge being 12.6, which is really high cubic feet per second. And also an important factor is reduction in in nitrogen load. The nitrogen load from natural cover meadow is 2.2 pounds per acre per year, but similarly, from impervious cover parking lot, it can have runoff accumulating nitrogen from different areas in the watershed, around like 15 pounds per acre per year. Just an example of what can happen with the nutrients. Time for another poll.
All right, it looks like most people have answered. 8% of people say road salt and high chloride levels. 41% of people say nutrient loading, phosphorus and nitrogen. 40% of people say sediment and trash accumulation. And 11% of people say heavy metals and oils from the first flush events. And just because a couple of people have reached out to me saying they're unable to read the polls, all of those responses were in response to the question, what is the most persistent water quality concern you face at your plant or in your watershed?
Thank you, Louis, so much for taking care of that. Yeah, nitrogen and phosphorus loading is kind of one of the major issues. We'll see in next few slides that how green infrastructure can help that. We have already talked about like smart salting strategies, so it can help with reducing those salt and chlorine concentrations as well. So let's talk about existing infrastructure and green infrastructure. Stormwater practices traditionally are interventions designed to reduce either runoff volume or improve runoff quality or both. And historically speaking, like stormwater management kind of focused almost entirely on flood control, moving water away from streets and building as quickly as possible. But we have learned that speed is not always the solution. It can cause problems downstream. So by accelerating runoff, green infrastructure increases peak discharge in receiving streams, which can again lead to stream bank erosion, sedimentation, and habitat degradation. So modern stormwater practices came into place, combining green and gray infrastructure, aiming to restore the aspects of like natural hydrology. So instead of simply conveying water, they encourage infiltration, storage, filtration, evapotranspiration, which all help in improving the water quality. And for small systems and communities, especially, the goal is to kind of implement cost-effective measures that reduce both, again, the infrastructure strain, which is already in place, and then improve our watershed and reduce its degradation. And it's really important, I believe, to think of these practices not as isolated installation, but as components of a broader watershed management strategies. The most like successful programs that I have seen kind of layer multiple approaches across these neighborhoods, public facilities, and transportation corridors. So there are two different type of practices that we see: structural practices, which include detention and retention basins, swells and bioswells, rain gardens, permeable pavements, and constructed wetlands. And then there are some non-structural practices which focus on behavior and maintenance. Examples for that include sweeping, erosion control, enforcement, construction site inspections, and things like that. And like most, again, speaking, that most effective programs combine both of these approaches. There cannot be an isolated single approach that can help you like win this argument. So you have to combine multiple approaches to improve your water quality and reduce runoff and things like that. So we hear a lot of terms on green infrastructure. There are different buckets where we can put our green infrastructure in. We have all heard about terms like nature-based solutions, green infrastructure, low impact development, and I think this figure does a really good job of putting these assets, different assets under different categories. Natural assets which can already just exist like rivers, lakes, and streams, but all of these assets in combination kind of we read about enhanced assets like rain gardens, bioswales, and so all of these assets in combination can be categorized as green infrastructure. And for many communities, like green infrastructure will be a complement to green infrastructure. They can be not like we should not be thinking about this in isolation. So it will be a combination or complement to the green infrastructure that already exists. So if systems do not blend like both type of assets into a single program or single management strategy, opportunities to use this green infrastructure to save money, improve our environment, and increase efficiency could be lost. And green infrastructure is particularly valuable for like small communities because it can be distributed, it can be in different parcels, and it is really scalable as well. So for example, a single rain garden won't transform your whole watershed, but dozens across the neighborhoods can obviously collect water, stormwater, reduce your peak flow, and reduce your pollutant transport as well. And green infrastructure also provides visible community benefits. Residents can see the rain gardens, tree plantings, permeable walkways, and this kind of builds your public support in ways I don't think so like the pipes underground could do. And it also provides benefits and benefits for climate variability and resilience, and with increasing infiltration and reducing flat flooding. Another poll. I think this would be the last one, but I can't promise.
How familiar is your team with designing or maintaining green infrastructure, bioretention, permeable pavement, etc.? We'll give people a little bit more time to get their answers in. All right, it looks like most folks have answered. 53% of people say they're just starting to learn. 32% say they have some projects in place, and 15% say they have a robust, established program.
I think it's a really good response that we have people who are still in learning phase, and I think this presentation would help you in getting some resources to do that. Let's see some common practices in more detail. Rain gardens are shallow vegetated. You can see in the image, depressions designed to collect runoff from rooftop or parking areas. They use soils to filter pollutants and promote infiltration. Proper plant selection, especially like salt tolerant species in colder climates, is really essential to make this work. And then we often see permeable pavements, which allow water to pass through the surface into a stone reservoir beneath. This reduces runoff and can reduce like winterizing as well, help with that. However, maintenance is really critical for all these green infrastructure components. Then there is an example of vegetated swell. It can help replace concrete channels with planted conveyance system. They help slowing in runoff, and especially if a lot of people are struggling with nitrogen pollutants, it can help allow infiltration and help with denitrification as well along the flow path. And each of these practices reduce peak flow and again pollutant transport while enhancing the community resilience as well. We have some other green infrastructure like rain barrels, which are usually kind of connected directly to buildings and facilities to capture that runoff water from the roofs and use that for further purposes like landscaping and things like that. Uh, just an image to show another example of green infrastructure of bioretention. This is just a cross section of how it is structured or layered and how it can help with filtering out your water or capturing those pollutants. And green infrastructure often acts as a buffer between developed areas and receiving water. So by slowing water and infiltrating runoff, green infrastructure can help reduce inflow and infiltration into sewer systems, decrease your peak wet weather flows, and reduce like shock loads to biological treatment process if it's a combined system. So for small systems and communities, this effect can extend the life of treatment infrastructure, lower peak mechanical stress on pumps and clarifiers, and reduce pollutant loads as well. These are some co-benefits of green infrastructure. I'll just like briefly mention that you can use this graph or use this image for competing for grants. Highlighting co-benefits can really make proposals significantly more competitive. So please highlight that when you are applying for any grant or any opportunity for funding, because these can really strengthen your funding application because of multi-dimensional impact. Again, just an example to show from a toolkit, Green Infrastructure Toolkit for Wisconsin municipalities. It shows an average stormwater holding capacity, which describes the volume of water each of these practices that we mentioned recently could hold. Again, this is based on basic assumptions, and these are assumptions that worked for Wisconsin or that are modeled for Wisconsin municipalities. But again, you can use a similar kind of numbers based on rainfall and use these assumptions to at least do back of the envelope calculations on how much annual stormwater runoff reduction you can do with your green infrastructure in a particular parcel. This is the last one.
Which green infrastructure practice do you believe has the highest potential for success in your specific community? Make sure to get your answer in. All right, looks like most folks have voted. 41% say bioretention and rain gardens, 16% say permeable pavement, 20% say tree planting and canopy expansion, 8% say water harvesting in rain barrels or cisterns, and 15% say wetlands.
Yeah, all these infrastructure are really great with a lot of co-benefits as well. So I'll just quickly skim through MS4 permits and their overall requirement because we are kind of running short on time. MS4 permits are designed to reduce urban runoff impacts on water bodies. They established a framework for managing stormwater through public education, illicit discharge, post-construction management, and things like that. MS4 programs are kind of proactive watershed protection programs. They recognize that urbanization obviously increases, we saw with different examples, increases runoff and increases pollutant loads. So therefore requiring municipalities and small communities, some communities to implement some of the preventive strategies. There are different minimum controls measures required under MS4 permits, which include public education and outreach, public involvement, illicit discharge detection, construction site runoff, post-construction stormwater management, and good housekeeping for municipal operation. These are all required usually under all the MS4 permits, either it's phase 1 or phase 2. Most small municipalities or small communities come under phase 2 permits. It is so compliance for MS4 permits involves regular inspections, documentations, reporting and interdepartmental coordinations, which is really crucial. And operators or planners can play an important role in identifying like unusual wet weather flow patterns, assisting with outfall inspections, and documenting the impacts of the storm, and early detection of these cross connections or illicit discharges or inflow infiltration can help like prevent regulatory violations as well. So I just wanted to highlight like two of these minimum control measures because I feel they get some usually less attention than others. So public behavior obviously significantly influences into stormwater quality, like improper disposal of chemicals, pet waste, and trash directly affects runoff quality. So engaging the public and communities reduces contamination at source or holds it at source. And some of the effective strategies to do that would be community cleanups, uh, school partnerships, open houses, and social media campaigns. All of that can contribute to like build awareness here in Maryland and Prince George's County. We also run at University of Maryland Environmental Finance Center. We also run a program on basically doing that, providing education and outreach to communities on the name of the program is Climate Steward Academy, where participants come and do a stormwater do a project as well in the end while learning about the program and stormwater management impacts and things like that. So again, another MCM is on stormwater education and outreach. You can have key messages like only rain down the drain are like, I feel simple but really powerful. Your outreach materials, if you're a municipality, should be clear and actionable. It could be translated into a different language as well if there is need for that. And operators or stormwater managers can use like short videos to do demonstration at community events on how this infrastructure kind of works or what are the impacts of that, and like partner with community-based organizations or conservation districts to increase this education and outreach as well. We now transition to practical tools that support planning, design, and funding. I think for the sake of time, we'll kind of skip this poll. This tool is called How's My Waterway. I think it is really useful tool and one of the most powerful starting points for understanding your watershed conditions. It is an EPA developed publicly accessible platform that allows you to enter your zip code, city, or water body name, and you can immediately see the condition status of like local streams, lakes, and rivers. It also provides you data on overall quality of your watershed, how are conditions for swimming, aquatic life, drinking water conditions, and things like that. It also has data from water monitoring and extreme weather events we can see on the screen as well, like total precipitation that happens in that area, drought days, and things like that. So and you can also project other data if you have using this tool as well. So if you are a community planner or looking to see how it impacts overall impacts on your community or at a watershed scale, you can definitely check this tool out. Green Infrastructure Wizard, again, it's EPA's centralized clearinghouse for green infrastructure tools, research, case studies, and design sources. It's not like a modeling tool itself. Instead, it helps you navigate the landscape of like available tools and technical guidance, like whatever is available. And like I feel this tool is really crucial because it houses all the information in one place. And sometimes for communities, it is kind of like biggest barrier to access like what already exists. And this tool organizes information, whether you are looking for planning support, cost analysis, performance modeling, and case studies from like similar communities. So when you are developing a grant application or working on a stormwater management strategy or green infrastructure strategy, this can help you identify technical documentation to strengthen your proposal or provide you extra information on how to better design your stormwater management or green infrastructure strategy. This is a National Stormwater Calculator. I really like this tool because it's an analytical tool. It allows you to estimate runoff from a particular area, check your retention performance for a specific site. So your input would be You'll be inputting location. It will help you determine soil type based on the existing data the EPA has. It is most of the times accurate. It will help you with topography. You can see like overlay map and like attach different percentages to that. It will help you with precipitation data. It will point out nearest weather station and get the weather data from that. And then you can like kind of test different low impact development scenarios and controls like rain gardens, green roofs, permeable pavements, and compare runoff volumes. In the next slide, I'll show you how how you can see that or determine that. And I think this is really valuable during planning and design phases instead of like guessing how much runoff reduction a practice might achieve or doing like manual calculations for that. You can model it using this tool, and it also includes like climate change scenarios. So you can project your future precipitation projections, and also includes like cost information. Obviously, that won't be that accurate, but it will give you at least an idea of how much it could cost, like that particular strategy that you are trying to implement. And it can also like help you strengthen when again you're applying for any grant application. It can strengthen your proposal for that. Again, this is a scenario from that. We can see in the image that largest rainfall without runoff in current scenario is 0.42 inches, but with the baseline scenario, when I made all these changes of changing 20% of runoff into rainwater harvesting, or having 20% of area as a street planters on infiltration basins, how it impacts the different scenarios of controlling runoff and reducing peak flows. Similar tool to previous one, it's green value stormwater management calculator. It shows you like for different property sizes or different lots, you can calculate again based on rainfall data. You can add green improvements like I've added here. So I've added like parking lot swells, rain gardens, rain barrels. So it shows me that it can help based on the design storm that I chose for 2 inches. I believe it's going to help capture almost more than 45% of that, and it will cost like 20,000. It shows like other hydrology and runoff metrics as well. How it like with and without best management practices. It can also estimate like increase in real estate values and things like that. So it is really a useful tool again if you are looking for any initial planning and things like that, or doing any planning for small scale project as well. This is a great database and resource for understanding like design, construction, operation, maintenance, and costs associated with implementing green and natural infrastructure. It is hosted by EFCN, UNM EFC, and it provides detailed information about green infrastructure options such as green roofs, bioretention, infiltration basins, and obviously these all kind of require maintenance. So it is really important to have that plan in place to do regular maintenance of that, and this database can help your communities and you to catalog like green assets and track their maintenance schedules and things like that. I found this, I've shared this example before in previous slides as well. I've linked all these tools and toolkits and resources, so you can download the slides and review that as well. This is again a modeling toolkit for municipalities. It not only it has information on different green infrastructure, but it also has information on like policy considerations or permitting and things like that. So it's really useful for identifying those barriers and how to overcome that. These are technical design guidelines such as Denver's Green Infrastructure Guide. So if you're looking to look more into depth on how to design the green infrastructure systems, you can again go to this website and download this. This is pretty detailed on and shows really good visuals on where to install it and the sizing and things like that. So it was really useful again if you're planning or any green infrastructure improvement project. I think that's all from my side.
All right, it looks like we've run out of time for questions, but I will share the questions that were already submitted to me with Danish, and if he has the capacity, we might include them in the follow-up email. For now, huge thank you to Danish for sharing your expertise with us today. Following this webinar, you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following the webinar so that you can let us know your thoughts on today's session, as this helps us plan future webinars on topics important to you. Thank you again, and we hope to see you at future EFCN events. Have a great day.